All right, so chapter 4 deals with forces. Anyone have a description for me of what a force is? Or a guess? Force has a really general definition. A force is any time a push or a pull is exerted on an object. That's it. Anytime there's a push or a pull on an object, it is considered a force. So give me some examples of types of forces that we know. Can you think of any types of forces that we might know already? Anything you can think of? All right, we'll get to there. We have to make, it's okay. It's okay. It's not something that we would usually even think of as a force, right? Gravity is an acceleration that causes a force, right? There's a gravitational force that moves things. Anytime we actually push or pull something, right? If I move this with my hand, that's just called an applied force. I'm applying that force. So there's a lot of different types of forces, and I'm going to give you a table that's got all that laid out for you. But let's just give some general things first. So a force is anytime we push or pull. How do forces affect the motion of an object? What do you think forces could do to an object? Can forces speed them up? Bless you. Yeah. Can forces slow things down? Yeah. Can forces make something change directions? Yeah. So it could do all the things, right? Forces that speed things up might be gravity. Gravity's pulling something to the ground. It could be an applied force. Forces that slow things down could be air resistance, could be friction, right? Could be any applied force, a brake or something. And then changing the motion is just going to be any of those things as well, right? Mostly an applied force. But it can do all of those things. It can speed up, it can slow down, or it can change the direction of the motion. These are two vocabulary words that I just want you to be a little bit familiar with. Your book uses these terms. I won't use them a whole lot, but I want you to be aware of what they mean. The system is the object that is being manipulated. It's the one that is doing the changing. That is being changed. And then the agent is the object that's causing the force. Okay, it's the reason that something is happening. Newton has three main laws that we're going to talk about. Any idea on the first one? It's very famous. Newton's first law is called the Law of Inertia. The Law of Inertia. And it basically says every body continues in its state of rest or in its state of speed until it's acted on by a non-zero force. Okay, and this is the way we usually abbreviate that law of inertia. And it means bodies at rest tend to stay at rest. Bodies in motion tend to stay in motion. You don't have to write out the first one necessarily, but I would have at least the shortened definition that you have an idea of what it means. Okay, and I would maybe also write down the nickname for it, which I'll write up there as well. It's the law of inertia. All right, so this is nicknamed. The very first law, Newton's first law, is called the Law of Inertia. The Law of Inertia. That's kind of the nickname. Inertia, what inertia means, it's the resistance of an object to change. Okay, it means an object's resistance to change. So that means if an object is at rest, is it going to randomly start moving? If it's at rest, is it going to randomly be put in motion? No. If it's going to be put in motion, something has to push it or pull it or move it in some way, right? If an object is in motion, something has to make it come to a stop, or something has to make it slow down. If nothing were happening, if we were looking at perfect physics world, no friction, no air resistance, no nothing, an object would just keep moving in a straight line until it runs into something. Right? That's the law of inertia. So inertia means the resistance to change, which just means if they're at rest, they want to stay at rest. If they're in motion, they want to stay in motion. All right. Sorry, I already said all those things. Inertia is the tendency of an object to resist change. That's all that means. Okay? So forces are vector quantities. Vector quantities, they have to have a magnitude and a direction. And how do we draw vectors? Using what kind of shape? A straight line, not quite a straight line, kind of a straight line, but what's it have on the end? An arrow, right? We represent vectors with arrows. So we do the same for forces. Forces are represented with an arrow. Just like we did with displacement vectors or velocity vectors. The direction of the arrow is in the direction of the force, whether it's being pushed or pulled or going upward or downward. Same thing we've done with all of our vectors up to this point. Right? They should be in the direction of the motion, or more specifically, the direction of the force. And we're going to do our best to draw them to scale. Okay, roughly to scale. So I want to give you just a little picture of what I would, of an example of how we draw forces. So we've got our object here in the middle. I'm just going to draw it with the dot. And you don't have to draw this. I just want you to kind of see what's happening. Let's say I pull on this object to the right with a force of 50 newtons. The units for force is newtons, and we'll get there in just a minute. But let's say I pull on it. That's like a tug of war situation. We pull on with 50 newtons to the right, and we pull on it only with 20 newtons to the left. Which direction do you think my object will move? Left or right? Right, right? I'm pulling on it with the right side with more force. So in this case, what would my net force be? Knowing what you know about net, anything else, what would my net force be here? Yeah, it would be 30, right? I take 50 to the right, minus 20 to the left. My net force would be 30 newtons to the right. Does that kind of make sense how we found that? We're going to do a lot of examples of that. But that's the whole point of these force systems and these drawings, is that they give us an idea of how do we find the net, right? Net means the sum total of these things. All right. Our unit for forces is newtons. It's given with a capital N. It's given with a capital N. It's an abbreviation of a force. That's kilograms times meters per second squared. That's the unit, and they abbreviated it by calling it a newton. Okay? So capital N. So when we see that capital N, we don't want to be thinking north, right? It's going to be newtons as the unit for that. Sometimes they'll be north, but not always. All right, types of forces. I have this table here for you. I'm going to give you, I don't want to talk too much about this. There's two main types of forces, a contact force and a field force. And all you really need to know, you don't necessarily have to have the examples of these. Contact force just means a force that makes contact with the object. That's it. It touches the object. So this would be anytime we push, we pull, we hold something. Anything that is making contact with the system is considered a contact force. And then a field force is anything that does not make contact with it. Okay, so example of field force would be gravitational force. Another field force, I would consider air resistance a field force. I'm not sure if I'm exactly right on that, because technically the air is touching the object, but I think that would be considered a field force. Magnetic forces, those are considered field forces, all that kind of stuff, where you're not actually making contact, but still having an effect on the object. Okay? Contact forces are any time we actually touch the object. So friction is a contact force. Do you know what friction is? Friction is something that interacts between two surfaces. It causes them to slow down, right? Friction is like the interaction of two surfaces. All right, so let's see here. When we talk about our forces and when we look at all of these different forces put together, our goal is really going to be looking at the net force. And net means the sum of all the things, right? The sum of all of our forces added together. It is called the net force. Okay? Sorry, give me just a second here. On net force, we're going to start labeling all of our forces with a capital F, right? All forces are labeled as a capital F. If it's Fg, that would be like a gravitational force. F applied would be any sort of applied force like that. I write it like APP. And then if I'm going to look at F net, I just write it down as a little subscript like that, right? We can label our forces with just about anything, but you'll see that these are kind of common ones that we see. Okay, the net force means that I'm looking at the sum of all of my forces put together. All of the other ones are just really individual forces. Okay, we're going to start putting them into some diagrams here in a second. All right, last thing we need to know about net force is that when we are at what we consider equilibrium, that means my net force is 0. My net force is considered 0 or at equilibrium when my object is either at rest or at constant velocity. Okay, so I want you to make this little note too. Object is at equilibrium, which means F net equals 0. When my object is at rest, or when my object is moving at constant velocity. Okay? What questions do we have so far? All right, our goal for this chapter is going to be calculating F net a lot. We're going to be looking at net forces in the vertical direction and in the horizontal direction to kind of be able to identify what's happening to our object. Okay? So we're going to look at how we draw vectors and how we draw forces. We already said they're represented with an arrow, but the diagrams that we use to show forces are called free body diagrams. Free body diagrams. What free body diagrams do is they allow us to make a model of our system. It allows us to look at what is happening in our system. You don't have to necessarily draw this, but I'm going to show you an abbreviated version of this here in just a second. Okay? So what free body diagrams allow us to do is make a model of our system. It tells us every place that the system is being affected by a force. Okay? It shows us everywhere the system is touching the external world. So any forces that are acting on it need to be displayed in our free body diagram. When we draw forces, we draw them in the direction of the force stemming from the object. So I'll show you here in just a second what that means. Here's our system. We've got a book on a table with a hand pushing that book. Now, does that make sense? So the first thing that we do when we draw a free body diagram, and I'm going to draw my own down here at the bottom. First thing that we do when we draw a free body diagram, you're welcome to draw the picture. You really don't have to, right? I always identify my object just by a dot, like you see they did right here in the middle. Okay, identify my object as a dot. And then every force that is applied to that object needs to be drawn on that diagram. But you'll notice we don't draw our forces like this. It's being applied to the right, so we put it like that. That's not how it works. It has to stem from the object and move to the right. Okay? Since this is they called it the force of the hand on the book. I would never take that much time to write out that much abbreviation. That's silly. Okay? All I'm going to call that is I know I'm applying a force to that book. So APP is how I abbreviate applied. right? This is the force we applied. That's it. You can call it FP for force push, or you can do it however you want. But you'll see most of the time I label it as applied. All right, so that's really the only force that is visible to us, right? But what do we know is always acting in the downward direction? We know that gravity, Fg, is always acting. So Fg is the force due to gravity, or the gravitational force. Both of those names mean the same thing. They call it the force of the Earth's mass on the book. That's way too wordy. We know that the Earth pulls things down toward it, and it's called gravity, right? So we just need to label it as Fg. The last force that is being applied here, we haven't talked too much about yet, but we need to think about really Newton's third law a little bit earlier than we needed to originally. But Newton's third law says, for every action, there is an equal and opposite reaction. Okay? But let's think about this. Is my book falling through the table right now? Is gravity pulling down on it enough to make it fall through the table? No. Which means there must be some upward force keeping that book up, right? Holding it on the table. So the force that's being applied by the table on the book is called the normal force. F and then a capital N is for normal. Okay? So we call that the normal force. And what the normal force is, we're going to go into this more in a little bit, but what the normal force is that it basically counteracts gravity, right? But it only happens when something's on a surface. It can be the ground, it can be a table, it can be whatever it is, but it has to be on a surface for the normal force to apply. Okay? What questions do we have there? We want to try to draw them to scale, and we want to make sure that we've got them coming from the object and pointing outward. Okay? In this case, do we know anything about these two vectors, the normal force and the gravitational force? What do we know about them? Are they equal or are they not equal? Yeah, they're equal because my object is not accelerating up or down, is it? The only place it's moving is to the right. So if you want to in your diagrams, you could start putting a little congruency sign in there to show you that these two forces are equal to one another. Okay. Last thing here that we need to think about is my object is going to be accelerating to the right or moving to the right. And in this case, we didn't account for friction, right? Do you know what friction is? Right? We said it behaves between two objects. It always happens opposing the motion. So if we were going to show friction on this diagram, it would go in this direction like this. We'd have a frictional force, lowercase f, that would go in that direction. We don't have that in this picture. It tells us to put friction, so we just ignore it unless it talks about friction. But we could have that if we needed to. Okay. All right, let's do some practice free body diagrams. All right, draw the free body diagram of a box accelerating in the rightward direction. Include frictional forces. So that's kind of just the idea we were talking about. So let's draw our free body diagram here. We start with a dot, right? This is our object. Okay, first thing I want you to think about, what's always included? Gravity, right? Because this thing, it's not on the moon, right? It's got to be on Earth somewhere. And it says it's accelerating to the right. So it's got to be sitting on something. It can't be suspended into the air. So if we have gravity, what has to counteract that? The normal force, right? And is my box accelerating in the upward or the downward direction? No, which means these two forces have to be equal to each other, right? Think about this. In the vertical direction, F net, in the vertical direction, my net force would be 0. Right? Because my positives equal my negatives. Does that kind of make sense with that? Okay. Now for the horizontal directions. It says it's accelerating to the right. Okay, it's accelerating in the rightward direction, which means I've got some sort of applied force to the right. Doesn't really matter what it is. Something's being applied to the right. But it says I need to include frictional forces. So is my frictional force going to be equal to my applied force? Or do I want it to be greater than or less than? Less. Good. I want it to be less than. Because I don't want my object to be moving at constant velocity in the horizontal direction. I want it to be accelerating in the right direction. Okay, accelerating to the right, which means my rightward force needs to be greater than my frictional force. Does that make sense? Okay, so this diagram is correct right here. What if my diagram looked like this? What if my diagram looked like this? Here's F applied, and here's my frictional force. What if it looked like that, and these two lines were congruent? What would that, I have two scenarios about what could be happening there. I could be moving at constant velocity, or I could be at rest, right? Those are my two options. I could be at constant velocity, or I could be at rest. And then the last option for this is, what if my applied force looked like this, and my frictional force looked like this? What would I be doing? I would be slowing down, right? Friction would be causing me to slow down, or I would be at rest. I have two scenarios there. And since we don't know the numbers, we're not sure exactly what the scenario is. But if my frictional force is greater than my applied, that either means I'm not applying enough force to get it started, or I'm in the process of slowing down. Okay? Do you see the kind of difference there? All right, so this one says a car is coasting in the leftward direction and slowing down. Do you know what coasting means? Coasting means you're not applying the gas in your car anymore, and you're not applying the brake. You're just letting it roll. Does that make sense? So you're not applying a force to make it go forward, and you're not applying the brake. So here's my object. I have to know I have gravity and the normal force because they're equal to each other, right? My car is not accelerating in the vertical direction. Okay, am I applying any sort of forward force here? I'm moving forward, but am I applying a forward force? No, right? So the only thing that's slowing me down is friction. Right? I'm not applying the brake. I'm just letting my car roll, and the friction between the tires and the road will eventually slow me down, right? So the only thing that's happening here is that I've got a frictional force that's slowing me down. So my frictional force is opposing my motion because I'm assuming that my car's moving forward, moving to the right. Right? It doesn't say that specifically, but if it doesn't give us a clue, we're going to assume our car's moving in the positive direction. That means friction has to oppose the motion. Yeah, good question. All right, so now we've got an idea about how to draw the pictures. Let's look at some calculations now. We're going to find net force. All right, so let's look just at this first example here. You don't have, if you want to write them down, you can. You don't have to. That's up to you. This first diagram, I've got an object that's being pulled on by 100 newtons in both directions, which means my net force is equal to 0 newtons. Does that part make sense to everybody?
All of this like one is
These are just 3 different scenarios. Yeah, 3 different ones. All right, so to find our net force, we take positive, minus negative, and we get 0. So in the second object, they have them drawn as separate forces, but if this were my diagram, I would have drawn it to look like this. Here's my system. I've got 100, and then I've got another 100. And so if I go to look at this, I would say F net, my stylus is looking. I would say F net equals positive forces minus negative forces, which I don't have any negative forces in my system here. Right? Here's my system. I don't have any negative forces, but I do have to add together my positive forces, so I get positive 200 newtons for my force. Okay, last one here, I would say F net equals positive, which is 100, minus negative, which is 200, which means my resultant or my net force is negative 100 newtons, Or you could say 100 newtons to the left if you want to draw it like that. Okay, does that make sense on how we calculate net force? Okay, it's always positives minus negatives. That's the basis of how we calculate net force for the whole chapter. Our problems are going to get a lot more complex than that. They're going to be we're going to start doing X and Y for all of these things. But at its very basis, we're going to take positive forces minus negative forces. Sure. Maybe. There? Newton's first law was law of inertia. Objects at rest, stay at rest. Objects in motion, stay in motion. Newton's second law basically has a whole lot of wordy explanation to get to this equation right here. Force equals mass times acceleration. Okay, that's really the takeaway for Newton's second law. And all this is doing is saying this equation in sentence form. Okay? Acceleration is directly proportional to the net force acting on the object, and it's inversely proportional to the mass. So the way I would like for you to write this is really to say F net equals m times a. That's going to be a better way for us to really work with Newton's second law, is the net force is equal to mass times acceleration. Okay, so now we've got two ways to solve for the net force. The first way is to take positive forces minus negative forces. Second way is to take mass times acceleration. So there'll be a lot of times where we substitute these two things together, right? That's going to be how we solve that very often. So F net equals ma should be our equation really for this chapter. We're not going to get a new equation sheet really for this chapter. This is almost the only equation that we'll use, and then the positives minus negatives. But that's not something that we set up on an equation sheet. It's just a practice we'll use. Okay, so let's try one here. Sorry, all right, F net, we were talking about that. All right, find the net force of a car if it's accelerating at 4.9 meters per second and it has a mass of 1,000. So this is literally as easy as it seems. We don't really need to know if there's friction or what the applied force is. All we want to find is the net. So I'd say F net equals m times a. Right? We don't really care in this case, right? If I was going to draw the free body diagram, I don't really know. Is there friction? Is there not? I know there's a normal force and I know there's a gravitational force that are equal to each other, but I don't really know what's happening horizontally. And in this case, it really doesn't make a difference to me if there's friction or if there's not. Right? All I need to know is that it has a mass of 1,000 and it accelerates at 4.9 meters per second squared, which means that my net force is 4,900 newtons, right? This acceleration is taking into account any other force that's acting on it, right? This is its resultant acceleration. So that's really all that's important for us, okay? Let's try another one here. What net force is required to bring a 1,500 kilogram car to rest from a speed of 100 kilometers per hour within a distance of 55 meters? Okay, our net force equation is this. And then, do you see any issues here? We have the mass. Oops. We have the mass, but is this an acceleration? No, it's a velocity. So we need to first solve for acceleration, and then we can solve for net force. So how do we solve for acceleration here? I'm given initial velocity, I'm given distance, I'm given final velocity, right? So you might need out your kinematics. Okay, you don't have to necessarily grab that out right now. That is something that we might need through this chapter. But if I'm given my initial velocity is 100 kilometers per hour, I need that in meters per second. So let's do that conversion. which is 27.78 meters per second. My final velocity is 0. My x final is 55. I don't have time, so I'm probably going to use my third kinematics. 0 squared equals 27.78 squared plus 2. We're solving for A, 55. So my acceleration is negative 7.01 meters per second squared, I believe. Okay. And so once I have that, I'm going to be able to take this and my mass and solve for my net force. F net equals 1500 times negative 7.01. And I get a net force negative 10,521.9 newtons. So what does it mean to us that our force is negative? It just means that it's opposing my motion, right? And that makes sense. If my car was moving forward and was brought to a stop, that had to have happened because of a negative force, whether that was a brake, whether that was friction, or a combination of the two, right? It doesn't really matter what all happened to slow it down, just that those forces added together to slow our object down had a value of 10,521.